To travel the land, one thing is prized above all else: speed. Since the fast production methods of Henry Ford put the world on wheels, speed has influenced every aspect of the car, and the car has literally shaped our world. In this episode, we surge from the once ubiquitous utilitarian Model T to the muscular V8 stylings of the Mustang, and from the jet-powered supersonic thrust to the electric game changers of Tesla. This is the story of land power. While only 29% of our planet is land, this is where we all live. And that 29% still equates to more than 92 million square kilometres to get around. 92 million square kilometres of mountains, ice, deserts, jungles, and everything in between. In order to efficiently traverse this vast terrain, often rugged and often inhospitable, man has evolved to walk upright. And the evolution has not stopped there. Today, this is where the evolution has taken us. The latest and greatest vehicle from a long-standing auto manufacturer, founded on the belief that nothing is too beautiful and nothing is too expensive. This is the Bugatti Chiron.
I believe they're in a league of their own. There's no one close to it for that level of hyper car.
The Chiron is the worthy successor to Bugatti's Veyron, the fastest street-legal car in the world, with a top speed of over 430 kilometres per hour.
The Veyron is a marker in the sand. It is the world's fastest car, and it will probably stay as the world's fastest production car for a long, long time to come.
The Chiron uses very similar technology to what was developed in the Veyron, and it's sort of a last hurrah for non-hybrid hypercars, where we have a nice big engine with 4 turbochargers and everything's mechanical.
With its speed electronically capped at 420 kilometres per hour, the Chiron, as the company likes to put it, brings beast to a very high level of beauty.
In terms of what they are, there's no electric motors or anything like that, it's still raw, brute power.
While its speed may be capped, the Chiron's 16-cylinder W configuration engine delivers a 25% performance increase over the Veyron, thanks largely to its 4 double-powered turbochargers.
They use W16 engines, meaning that you have W cylinder arrangement, and that can accommodate up to 16 cylinders in it, which is crazy.
With the engine mounted centrally in the car, more weight is placed over the rear tyres, increasing both acceleration and sensibly braking. Weight is otherwise kept to a minimum with a light and highly aerodynamic carbon fibre body. Defined by its sweeping C-shaped curves, these design features are integrated into the performance of the car, optimizing airflow to an engine that gulps a massive 16,000 litres of air per minute. Directing airflow is vital for speed, but in a car this overpowered, it's also necessary to keep it from flying off the road. Along the flat aerodynamic underbody of the car, a series of forward flaps adjust their angle at high speeds to keep downward pressure on the front tyres. The slit-raised wing at the back does the same for the rear wheels and serves as an air brake. With a multi-million-dollar price tag and taking an average of 6 months from construction to customer delivery, Bugatti releases around 70 Chirons per year, placing them among the world's most exclusive production vehicles.
No one will ever build anything like that ever again. It's a very iconic car in that sense. It's a one-off. You'll never see anything like that ever being produced, not on a mass scale. So it is a very, very special car.
More exclusive, though less luxurious, automobiles of various designs could be seen on the roads as far back as the early 19th century. The car has no single inventor. Rather, it's an evolution of the sum of an estimated 100,000 patents from dozens of inventors around the world. Experimenting with various forms of power, the first horseless carriages ran on steam, gas, or electricity, until one innovation steered them in a particular direction. Built by German engineer Nikolaus Otto in 1876, the Otto cycle was a compressed charge internal combustion engine that went on to define the dominant power source of automobiles for more than a century.
An internal combustion engine works by converting chemical energy into heat energy and then into mechanical energy. So by igniting a fuel-air mixture, we can increase the pressure within the combustion chamber, which drives the piston of the engine down. Now that downwards motion of the piston in turn rotates a crankshaft, and that crankshaft gives us rotational energy, which we can then use to drive the wheels.
While the concept of internal combustion engines had been around for many years, even after the technology was proven, it would be years before it was put into a car. To Carl Benz, we owe the first practical mass-produced automobile, the Benz Patent-Motorwagen of 1885. The three-wheeled construction featured a four-stroke engine of his own design, with an advanced electric ignition system and rudimentary steering. The motorwagon went on to become the first commercially available automobile in history, aided by a unique marketing campaign.
So internal combustion engine, the idea was there for hundreds of years, but then it was first commercialized and tested in a real vehicle by Mr. Benz and his wife.
Unbeknownst to Carl, his entrepreneurial wife Bertha took the vehicle and their two sons on a 100-kilometre journey to visit her mother, famously notifying her husband by leaving a note. This journey was the first long-distance drive, proving the viability of the automobile.
And that, by record, is the first driven internal combustion engine powered vehicle in the world history.
As cars continued to grow in practicality, they remained costly contraptions owned only by the rich. More than any other, one man and one car changed that forever. Henry Ford and the Model T. Born to a Michigan farming family in 1863, from an early age, Henry Ford showed an aptitude for mechanics. And after turning 16, he left farming life behind to pursue a career in engineering. Establishing the Ford Motor Company in 1903, Ford's vision was to manufacture inexpensive cars using skilled workers earning good wages. He did this by developing the assembly line technique of mass production. Installing lines of conveyor belts in his factory, Ford workers, who were paid a generous $5 a day, were at the height of production able to churn out more than 300,000 Model Ts annually. Offered to the public in any choice of colour, so long as it was black. The reason behind Ford's famous pronouncement was that Japanese black enamel was the only finish capable of drying fast enough to keep up with his production method. Model Ts could be put together in as little as 93 minutes, and these savings in time translated to financial savings for the customer. Because of Henry Ford and the Model T, car ownership in the US became affordable to the many rather than the few. And by 1918, half of all cars in America were Model Ts. Started via hand crank, the Model T's four-cylinder 20-horsepower engine reached a top speed of about 70 kilometres an hour, more than enough on the largely unpaved roads of the day. Utilitarian in appearance, uncomfortable to drive, and incessantly rattling, the Model T's many shortcomings were the source of many affectionate jokes. Nonetheless, this affordable mass-produced car is credited with powering a social revolution by providing independent transport to the masses. Ford would also be at the forefront of the next great revolution in automobiles, the V8 engine. First patented in France in 1902, the V8 engine was initially more common in speedboats and aeroplanes before it found its now iconic place in cars. The V in the V8 comes from the angle at which the 8 cylinders are mounted on the crankcase. Split into 2 opposing banks of 4, the cylinders drive a common crankshaft, which, as in a standard engine layout, converts the piston's linear energy into rotational motion that is transferred through the gearbox to the wheels. With the overlapping power strokes of the 8 cylinders largely eliminating unwanted engine vibrations, the V8 is an inherently balanced design. But the V8's principal innovation was that it generated more power without an increase in size.
By increasing the size of the engine, then you can produce more power. It is just a question about how to fit that certain volume that's large into a limited space.
Introduced in 1932, the Ford Flathead V8 was the first affordable, mass-produced V8 engine. The Flathead revitalized and redirected the Ford Motor Company. This engine whetted the appetite of power-hungry consumers, and the design of cars changed radically to keep up. From the V8, a new generation of car was born. While fast, overpowered cars had been produced before, it was in 1960s America that they went mainstream. With petrol cheap, the economy strong, and the youth market lusting for fast, sexy vehicles, the era of utilitarian transport gave way to a period of tire-smoking excitement in the form of muscle cars. These affordable small to mid-size cars, with their powerful V8 engines, could be driven for everyday street use, or pitted against each other in formal or informal drag races. With automakers competing for supremacy on the racetrack as well as the sales chart, the motto became, race on Sunday, sell on Monday. And this was the sales success story of the 1960s, the Ford Mustang. Coming onto the market in 1964, the Mustang, with its low price, good looks, and long options list, took America by storm. Although not initially marketed as a muscle car, the Mustang, with its optional range of gutsy V8 engines, certainly had the power to qualify. Instead, this high-performance compact created its own market category, the pony car. A huge factor in the Mustang's initial success was its low price point, owed to the fact that it shared much of its engineering with an existing Ford product, the Falcon. But it hardly mattered to the public. The Mustang offered enough stylistic points of difference to be its own car. Ranging from a 164 horsepower model to the high-performance version boasting 271 horsepower, the sales sensation of the 60s, the Mustang created a trend with the muscle car market that other automakers were bound to follow. Arriving fashionably late to the pony car party, Pontiac's 1967 Firebird made quite the entrance. Built with the specific purpose of competing with the Mustang, Pontiac had a little over 2 years to design and engineer the Firebird, which in car-making terms equates to a mad dash. To meet its deadline, the Firebird, much like the car it was striving to beat, started out by borrowing parts from existing vehicles, namely those of the Chevrolet Camaro. Chevrolet and Pontiac were both brands owned by General Motors, and both the Camaro and the Firebird were aimed at cutting into the Mustang's dominance over the muscle car market. Like the pony car it was made to compete against, the Firebird was offered with 6-cylinder engines as well as a range of V8s. And the V8s were by far the most popular. While the Firebird stirred the same levels of passion in its drivers, it never met the sales levels of the Mustang it was designed to tame. Remembered with the fondness beyond sales charts, the Firebird remains a much-loved product of the competitive spirit that characterized the muscle car era. Coming to an end in the 1970s, the period of muscle cars was short-lived, but their influence has remained strong and fed into other types of car. Cars like the Dodge Viper.
The Dodge Viper is an all-American action supercar. It is traditional, big engine, big loud, brash car.
Some engineers at Dodge had the great idea of stuffing the biggest engine that they had lying around into the smallest car they could fit it into, and the Dodge Viper was born. It's a point-and-shoot muscle car that will go incredibly quickly in a straight line.
First roaring onto American streets in 1992, this heavily muscled sports car and its voluptuous stylings pay loving tribute to the muscle cars of the early 60s. In a period where the prevailing trend was toward efficient, conservative cars, this gas-guzzling extrovert was a throwback to a different time. The chief selling point of this impractical vehicle was that it offered what few others in the more sensible 90s car market could: brute power.
It's got an 8.3-litre V10 engine, which is literally out of a truck, but they've transformed it into a performance car engine that just is brutal.
Recruiting the expertise of supercar manufacturer Lamborghini, which was owned by Chrysler at the time, the Viper delivered a rating of 400 horsepower at 4,600 revs per minute, numbers almost unheard of in the early 90s.
It produces about 480 kilowatts in its top spec, which is probably about 5 times the average small hatchback, and around the same sort of power as most of its supercar rivals.
Delivering great gobs of power to its extra-wide Michelin tyres, there was plenty of traction, and the Viper stuck to the road like the snake it was named after. Car lovers could not get enough, and the trend-bucking Viper, with its nostalgia for the muscle cars of a previous generation, was a top-selling instant classic. Before production vehicles were built and sold with race car power, the race for pure speed was long in the running. During the pioneering days of speed racing in the 1920s and 30s, few figures captured the public's adoration quite like Sir Malcolm Campbell. Holding the land speed record 9 times during his life, as well as setting 4 water speed records, the British-born motorist received a knighthood for his contribution to the field. Racing in a series of several cars he named Bluebird, the fastest of these was the Campbell-Railton model, built in collaboration with British automotive engineer Railton. A design of the modernist 30s, the Campbell-Railton Bluebird featured a low rectangular cross-section, spanning the full width of the wheels for reduced drag. Its distinctive tombstone radiator grille could be closed with a movable flap, briefly enhancing the aerodynamic profile during record runs. Powered by a Rolls-Royce V12 engine, the Bluebird made record-breaking runs across the hard-packed sands of Florida's Daytona Beach in 1933 and again in 1935. Clocking what was an unprecedented top speed of 445 kilometers per hour. Campbell knew the car was capable of more. Believing that a lack of traction on the sand was holding the Bluebird back, Campbell's quest for speed led him to the Bonneville Salt Flats of Utah. Here, on September 3rd, 1935, with his young son Donald watching on, Malcolm Campbell set his last land speed record of 484 kilometers per hour. Dying in 1948, Sir Malcolm Campbell was a rarity among the speed racers of his day, not only with his long list of successes on land and water, but for the fact he died from natural causes rather than in a crash.
Well, Dad, I'm mighty glad you reached the 300, but I felt sure you'd do it.
Right, old chap, I'm very pleased too. But I reckon you've had a real good time whilst you've been over here in the States, because everybody's been so awfully kind to you, haven't they?
They sure have.
Following in his father's racetracks, Donald Campbell set land and water speed records throughout the 1950s and 60s. While a generation before, his father Malcolm had been the first to break the 300-mile-per-hour mark on land, it was Donald's great ambition to go even faster, with his sights set on breaking 400. This was the vehicle that he hoped would do it, the Bluebird Proteus CN7, the first car to be powered by a gas turbine engine, an engine that up until this point had only been used in airliners. Drawing air into the engine through the car's open nose, this painstakingly streamlined vehicle was thought to be capable of over 800 kilometers per hour. Returning in 1960 to the site of his father's last record in Utah, Donald crashed during a test run at around 580 kilometers per hour. Thanks to the tremendous structural integrity of the vehicle, he survived.
I have survived the fastest crash that mankind has ever survived.
Despite being intensely superstitious, Donald Campbell's bad luck continued. With the car completely rebuilt, a more promising racing ground had been located on the dry lake bed of Lake Eyre in South Australia, a site that had gone without rain for 9 years. Shipping car and crew to the remote location in 1962, the heavens opened up and the lake was ultimately flooded to a depth of 3 inches. Finally, after 18 months of waiting, Donald made his courageous record-setting attempt on the still damp track. He achieved his goal, scraping past the 400-mile-per-hour mark and setting a new land speed record of 648 kilometers per hour. Never getting the chance to race on land again, Donald died 5 years later during a water speed attempt. From the early 60s, the land speed record climbed steadily higher, with the title of fastest man on Earth being traded back and forth between a handful of drivers. Californian Craig Breedlove claimed and reclaimed the honour several times before putting an end to things, at least for a while, in 1965. Using a surplus General Electric J47 engine, common in military aircraft, Breedlove's first record-breaking runs were not accepted by the International Automobile Federation because his vehicle, the Spirit of America, had 3 wheels instead of 4. After a near-fatal crash in 1964, the undaunted Breedlove returned a year later with the 4-wheeled Spirit of America Sonic 1. Powered by a superior J79 engine, he held the official land speed record for all of 5 days before it was surpassed. But the very next week, Breedlove responded with a new record of 966 kilometers per hour. This time, the record would last 5 years before being broken in 1970. To claim it back, Breedlove set his sights on going faster than the speed of sound. But he was not alone. This was the vehicle that Breedlove was up against, the Thrust Supersonic Car, SSC for short. Designed by a British team headed by Richard Noble, who himself set the land speed record in 1983, this jet-propelled car had the express purpose of not only breaking the record, but breaking the sound barrier.
If you want to go faster than the speed of sound on land, your problems actually are larger than in air, because you have the solid boundary, the Earth, on which you're traveling, and that means there is a very small gap between the moving object and the Earth.
Propelled by a pair of afterburning Rolls-Royce Spey 202 jet engines, the same used in F-4 Phantom fighters, the Thrust SSC produced an awesome 110,000 horsepower, making it the most powerful car ever built. Designing a car this powerful was one thing. Finding someone to sit behind the wheel was another. With a select few capable of the job, a rigorous testing process arrived at this man, Royal Air Force fighter pilot Andy Green.
It's like a man walking on the moon. It's the 4-minute mile. It's climbing Everest. It's something that nobody's ever done before. It's something that no team has ever done before.
Green's challenge was immense. Unable to house steering gear at the front of the vehicle due to aerodynamic restrictions, the thrust SSC was steered via its asymmetric rear wheels. Whether such an unusual system was viable at the speed of sound was uncertain.
From the aerodynamic point of view, make this very dangerous. You have this very slim cushion of high-speed air sitting underneath the vehicle, and there is a serious chance that this vehicle will be lifted.
Or if the nose were to dip, the car would drive itself into the ground. Everything hinged on having a perfectly neutral aerodynamic profile. Even if everything performed perfectly, the question of what happens when a land vehicle pierces the sound barrier remained unknown. There were fears that the resulting shockwave may derail or destroy the car, along with its driver. Nonetheless, in October of 1997, Andy Green and Craig Breedlove squared off in the Nevada desert to find out. Sadly for Breedlove, he never had his opportunity. With his latest Spirit of America suffering engine damage during a test run, he was forced from the contest and could only watch from the sidelines as Andy Green and the Thrust SSC took to the sands. 50 years and 1 day since Chuck Yeager and the Bell X-1 rocket plane first broke the sound barrier, Andy Green and the Thrust SSC joined the club, blitzing along the desert at a top speed of 1,227 kilometers per hour. This was the first time a car had gone supersonic. The record stands to this day, but it is not safe from attempts to break it. And Andy Green and the Thrust team are among those seeking to go faster still. Henry Ford is quoted with saying that auto racing began 5 minutes after the second car was built. With formalized racing events dating back to the emergence of gasoline-fueled cars, the racetrack has a long history of serving as a competitive testing arena, spurring continual improvements across all areas of vehicle performance.
The only race of its kind in the world, there were 49 starters in this year's Grand Prix.
More than any other, the world's oldest active endurance race, Le Mans, is credited with inspiring technology that has translated into consumer cars. Held annually in France since 1923, Le Mans has been called the Grand Prix of endurance and efficiency. Racing for 24 hours, competitors strive to cover the most distance around a circuit that mixes public roads with professional racetracks. With modern distances easily exceeding 5,000 kilometers, Le Mans tests not only a vehicle's speed, but its fuel economy, reliability, and safety.
Le Mans is an interesting race in that the engines have to be designed for both power and efficiency. Because it is such a long race, going for 24 hours, if your engine is inefficient, you'll be making a lot of fuel stops. And obviously, while you're stopped refilling your car, your competitors are going to be driving past you.
The long, fast straight known as the Mulsanne has fostered developments in aerodynamic performance. And with the unique safety rule that requires cars to be switched off while being refueled, hardier vehicles that can restart multiple times are de rigueur. Despite the emphasis Le Mans places on safety, deaths have occurred here, with the greatest tragedy being this crash in 1955, resulting in the death of 80 people. In response to the disaster, Le Mans, as well as other races around the world, enhanced its safety measures. But as safety standards improved, so did the power of cars, with vehicles adopting more extreme designs to attain more extreme speeds. Vehicles like the Porsche 917. The development of this now legendary car came about due to a rule change in motorsports that allowed for a new class of cars to enter endurance racing. With engine capacity capped at 5 litres, Porsche began work on a smaller engine version of its 908, and in just 10 months, the 917 was built.
Definitely the 917 broke all records and really made people have a look. Absolutely amazing car.
The car, in spite of its often garish 1970s paintwork, is today considered one of the greatest race cars ever made, and was even immortalised in film, starring alongside Steve McQueen in the 1971 movie Le Mans. But the 917 did not achieve instant greatness. In early models, the power of its 12-cylinder engine, capable of going from 0 to 100 kilometres an hour in 2.4 seconds, exceeded the vehicle's handling, and Porsche had a hard time finding drivers willing to pilot what was considered an accident waiting to happen. And at the 1969 Le Mans, the accident did happen, with driver John Wolfe losing control of his 917 and dying in the resulting crash. But Porsche persisted, and Chief Engineer John Horsman found the solution to the 917's problem. In studying the splatter of dead bugs over the vehicle following test laps, he noticed that the insects were concentrated on the bodywork, not the tail. No bugs meant no airflow, and therefore, no downforce. At high speeds, a race car's tail, or wing, is designed to do the opposite of wings on a plane.
Race cars tend to have downforce, so that is, they have aeroplane wings that are upside down that press the car into the surface, which increases the pressure that the tyre has to deal with, and they get very hot. So the slick tyres tend to be very strong construction and very sticky rubber compounds to keep the race car on the track.
With its lightweight aluminium frame and fiberglass body, the key to making the Porsche 917 into the dominant race car it became was in perfecting the design of the tail. Adding shorter, more upswept fins provided a clean flow of downforce-inducing air over the rear wheels. With a dramatic improvement in the car's handling, Porsche suddenly had a race winner on its hands. And in 1970, this car provided the German manufacturer with its first win at Le Mans. The following year was even more impressive, with the car again taking out Le Mans as well as 8 of the 10 races for the World Trophy, cementing the 917's enduring legacy as one of the most powerful street-legal race cars. With technology proven on the track, a class of cars emerged featuring the best performance and design the auto industry had to offer. Supercars. The term supercar has been used in the car market since the 1920s. Today, this is what it means. This is the Lamborghini Huracan. With its V10 engine delivering 610 horsepower, the highly powerful, highly luxurious Huracan can go from 0 to 100 in a blistering 3.2 seconds, securing it the honour of Supercar of the Year upon its release in 2014.
So it sounds amazing. I suppose the magician's back at the factory. A lot of it's with the engineering, with the exhaust and the manifolds and the way the sound gets delivered.
Using Aerodynamica Lamborghini Attivia technology, ALA for short, the Huracan bends air to its will. On the front, a horizontal splitter blocks air from flowing beneath the car, maintaining downforce on the front tyres. When downforce and the drag associated with it is unnecessary, a pair of flaps open in a split second, allowing air to flow through for improved aerodynamics. On the back, air intakes can direct airflow above or below the rear wing, again balancing downforce with drag. The wing itself contains a hollow chamber, allowing airflow to be directed internally to either side. When cornering at high speed, the ALA system directs airflow, and therefore downforce, to the inboard half of the wing, balancing the load on the rear tyres.
The Lamborghini Huracan engine is a V10, which means that there are 10 cylinders in a V configuration, 5 on each side. engine can produce 610 horsepower, which is equivalent to the amount of work 610 horses could do over 1 hour.
With its high power and high performance, the Huracan is an instant classic of the elite supercar genre. Not all supercars are created equal, and even in this rarefied world, it is possible to go one better. The best of the best. The top 1% of supercars are classed as hypercars. Cars like the Lykan Hypersport. Made by the United Arab Emirates company W Motors, this is the first hypercar of the Middle East. And carrying a price tag well in excess of $3 million, it is also among the most expensive production cars ever to go on sale. With a twin turbocharged flat 6 engine positioned behind the driver, the Lykan produces 750 horsepower. Going from 0 to 100 in a breakneck 2.8 seconds. The car's top speed is just shy of 400 kilometers per hour. With only 7 Lykans produced, they are among the most exclusive cars on the market, even by hypercar standards. Much about this enigmatic and excessive vehicle remains a mystery, including how many have been sold. Though it is safe to say that this is an extremely powerful car, owned by extremely powerful people. With supercars continuing to develop new technology and improve performance, for a vehicle like the Lykan to attain hypercar status, it must be at the very forefront of engineering and design. But the bar continues to be raised, and what is extraordinary today may be commonplace tomorrow. While it may be some time before diamond-encrusted headlights are standard, the innovations that have come from cars have the power to change the world. Literally reshaping the land, roads allowed cars to reach their full potential. And as cars came to travel faster and more frequently upon them, safety technology needed to accelerate to keep pace. First performed in the 1930s, crash testing quickly became a popular means of investigating a vehicle's structural integrity. With crash test dummies introduced in the late 40s, the impacts on a car's occupants became better understood, and this form of testing led to a suite of safety innovations. As the shortcomings of simple lap seatbelts were demonstrated, Volvo developed the now standard 3-point seatbelt. Rather than patenting the technology for profit, it was made freely available in the interest of saving lives. Airbags, unpopular at first, became more effective with improvements in seatbelts and are standard today. And as cars have become safer in accidents, the trend has shifted towards accident prevention, with a host of smart technologies designed to monitor driver performance or take over driving altogether. Just as it was in Ford's day, the greatest influence a car has is not the car itself, but how it is built. And today, vehicle manufacturing is on the cusp of a revolution, more world-changing than Ford's assembly line.
3D printing is a revolutionary engineering tool. It has the ability to manufacture quite complex shapes, layer by layer or in a blown system. So things like design complexities are not an issue anymore. Virtually anything can be manufactured using 3D printing.
Not only can 3D printing change the way we make cars, it can change the cars we make. With current methods needing to stamp out big pieces of metal into shape, cars are designed around parts that are mass-producible, not necessarily optimal. 3D printing offers a means of making optimal components mass-producible. With the freedom to add extra material to stress points for enhanced strength, or leave gaps to reduce weight, 3D printed vehicles are both stronger and lighter. But that is just the start. By customizing every detail of every car part, the possibilities of 3D printing are endless. Doing away with inflexible, mile-long assembly lines, small-scale factories will be empowered to produce an endless array of cars. With no need to retool an entire factory of machines, a 3D printer can go from making a truck to a small car with no downtime at all. Major manufacturers already use 3D printing to produce prototypes of vehicles that will later be produced en masse using assembly line methods. And with vehicle manufacturing one of the most environmentally damaging industries, the waste-reducing benefits of 3D printing promise a sustainable future for the auto industry. For cars to be truly sustainable, a new source of power is needed. Harmful to the environment and human health alike, the emissions from fuel-burning engines are increasingly being regulated by governments around the world. And as oil decreases in abundance, oil-derived fuels are increasing in cost. Fortunately, cars from their very inception have a history of running on alternative power. Hybrid cars decrease their dependency on fuel by incorporating an additional power source, typically electricity. Running an electric motor alongside an internal combustion engine, hybrids seek to improve fuel efficiency as a means of decreasing pollution and running costs.
Hybrid vehicles can be configured in a number of ways. The electric motor and the petrol motor or diesel motor can complement each other. They can work in parallel or they can work in series. So there's a lot of flexibility when it comes to designing a hybrid vehicle.
The first car to combine an internal combustion engine with an electric motor was constructed in 1898 by a young Austrian doctor with the familiar name of Ferdinand Porsche. 100 years later, the hybrid is back in vogue.
You basically have two power sources in any hybrid engines. The way they work is you have power split device right in the middle. And you have internal combustion engine running when it's needed to generate electricity, or directly linked to the power shaft and make the vehicle move. And this power split device sitting in can be used to control, either use that mechanical motion to generate electricity so that some energy can be stored in a battery, and then the electricity can be used when it's needed.
Electric engines also have the advantage of acting as self-powering generators, capturing energy that would otherwise be lost and converting it to electricity. This is particularly evident in regenerative braking. In conventional cars, brakes produce friction with the brake rotors in order to slow down, dissipating the vehicle's kinetic energy as heat. Regenerative braking slows the wheels by putting the electric motor into reverse. While running backwards, the electric motor is functioning as a generator, producing electricity and feeding it into the vehicle's batteries for later use. Economical and environmentally friendly, the long-known energy-saving technology of hybrids is today steering performance cars in new directions. A plug-in hybrid, the BMW i8 delivers near supercar performance with the fuel economy and emission standards of a compact vehicle. Marketed as the world's most progressive sports car, BMW claims the i8 is a vision of the future. And as the world's top-selling electrified sports car, they may be right. Chargeable via an ordinary wall socket, its high-voltage lithium-ion battery bank is maintained at an optimum operating temperature by an innovative cooling system. The turbocharged 1.5-litre three-cylinder petrol engine produces a healthy 230 horsepower. Sitting above the rear axle, the combustion engine takes a back seat to its electric counterpart.
BMW i8 approach, it's a little bit different. Your vehicle will be operated solely by AC motor, and internal combustion engine, it does not produce direct power supply to your power shaft, but it's more or less generating electricity, and then the generated electricity is used to run the AC motor. So the AC motor is the core element to produce power.
Obviously, the more motors you can have delivering power at any one time, the faster that car can go. It can be configured to just drive the wheels with the electric motor and use the engine as a generator. It's like carrying a power plant around with you in the car.
With an electronically limited top speed of 250 kilometers per hour, the i8 provides performance with impressive fuel efficiency and minimal emissions. With a choice of 4 driving modes, at one end of the spectrum, Sport mode makes the most of the petrol engine for maximum power. At the other end, eDrive relies solely on the electric motor, which can take the car for around 37 kilometers without using a single drop of fuel. The i8's highly aerodynamic design and its lightweight body, featuring carbon fiber reinforced plastics, adds to the efficiency and sports car performance. This is an energy-efficient, environmentally friendly vehicle that does not skimp on the power and fun of a traditional sports car. The need for a new source of power, reliable, sustainable, and affordable, has brought us to the cusp of a new era in automobiles. One car maker is counting on it. Tesla is both an auto manufacturer and a renewable energy company. Specializing in battery storage, it is the marriage of car maker and power provider that has seen Tesla lauded as the world's most important car company. Named in honor of Nikola Tesla, the genius Serbian engineer who invented the induction motor and alternating current power transmission, Tesla builds electric cars that don't just measure up to conventional vehicles, but outperform them. And with a maverick CEO in the form of Elon Musk, Tesla is using a business model all its own to make different cars for a different future. Tesla's first car, the Roadster, released in 2008, was the first high-performance all-electric car. Going from 0 to 100 in 4 seconds and able to travel more than 320 kilometers on a single charge. Constantly improving, the more recent Model S, with its ludicrous mode, goes from 0 to 100 in a staggering 2.7 seconds.
Essentially, the ludicrous mode on a Tesla just runs the electric motors up to their maximum rated power, which is inefficient, so it creates a lot of heat and it drains the batteries very quickly, but you can go fast. You can go very fast.
The key to this speed is the instant torque provided by the electric engine.
Torque is essentially the strength of an engine, or how much force it can put out, whereas power is the product of that force and the speed that the engine is turning at. So how many times per second that force is being applied is what gives us power.
The power advantage of an electric motor is its access to full torque from a standstill. Needing to force air into the engine for combustion, conventional engines have to build torque over a period of acceleration. For electric motors, the torque is produced not from the explosion of igniting fuel and oxygen, but from an electrical charge that winds the motor. Therefore, torque is produced the instant electricity is applied. Where once the internal combustion engine set a course for cars to follow and for innovators to build upon, today, the electric motor is set to overtake it. Tesla is building toward a world where electric vehicles will have levels of ownership beyond those of the Ford Model T. And as the revolutionary mass manufacturing techniques of Henry Ford put the world on wheels, now the radical possibilities of 3D printing are disrupting the established order. As we race ever forward, the story of how cars evolved in the past offers telling insight for their evolution in the future.